Okay, we will get started since it is already 3:05. So, welcome everyone to week 4 of this TA session for the course Optical Spectroscopy and Microscopy, Fundamentals of Optical Measurements and Instrumentation. So, as we already know, we are 4 weeks into the course, and we are slowly uh, getting into some key concepts for the course. We are almost at the end of establishing the fundamental concepts of the course. So the routine for this TA session is simple. So what I'll be generally doing is I'll be discussing with you guys about a general recap of the course, following which I'll just be going over some sample problems for this week, and in the end I'll also be discussing the previous week's assignment problems. For this week, last week, in week 3 we discussed about week one's assignment answers since the deadline was over. So for week 4, we'll be doing week 2. I chose to do only week 2 because I think there are already a lot of problems in week 2 itself. I think 15 or 16 problems. So we will go over them one by one. In the meantime, we guys can ask any questions if you have any doubts. So um, we will get started. We'll get started with the week's recap. So, can someone before I give a general recap of the contents of the week? Is it possible for anyone from the audience to give a short one line or two lines recap about what was the course contents for the past week? You can type it in the chat box if you are not able to type it out. Okay, it's fine. So if um, I'll proceed to tell the general recap. So for the past 3 or 4 weeks, what we have been trying to do is we have been trying to study the process of absorption as well as emission. In emission, we are studying about two processes: spontaneous emission as well as simulated emission. And we are in absorption. We are studying about the absorption of photons from a lower ground state to an excited energy state. So for the past before the week 4, for the past 3 weeks, what we have been doing is we have been trying to lay a foundation for the processes of absorption as well as for emission through quantum mechanical processes. So we were trying to bring in several concepts like the time dependent perturbation theory as well as Einstein's phenomenological approach to set characteristics or set expressions for different processes of absorption through establishing a perturbation Hamiltonian as well as an unperturbed Hamiltonian. In week 4, what we were doing is we took a slight diversion from the conventional time dependent perturbation theory as well as Einstein's phenomenological approach. And what we did was we discussed the findings of another such scientist known as Fogg. So this Fogg, what he did was he created a similar approach to solve the problems of absorption and emission. Basically, he tried to find the rate of absorption and rate of spontaneous emission through a quantum mechanical approach. So what he did basically was he took energy states, he took different energy states, and he tried estimating the absorption and fluorescence for phenomena by means of every single photon. So how he did that was we went ahead by taking particles one by one in different energy states. and he also came up with several operators which we can operate on, specifically the annihilation operator as well as the creation operator. So this might be a lot of the week four's contents, just like week three or week two, might be a lot of math for some of the people who have been going through this course, especially the ones who don't have a proper math background, instead have a instrumentation background or something like that. But what they were basically trying to do is they were trying to solve the perturbation Hamiltonian expression, and they were able to come up with expressions for the projection operator as well as for the rate of they were able to find out expressions for the rate of absorption as well as the rate of emission. So the rate of absorption, they were able to find out that the rate of absorption is kind of proportional to the matrix elements as well as to the number of particles in the kth state as well as the angular frequency and the Planck's constant. And on the other hand, the rate of emission, we can see that it was dependent on, it was proportional to the same set of parameters, but instead of nk, it was nk plus 1, meaning that even when nk is 0, they were trying, Fock as well as Einstein, they were trying to say that even when nk is equal to 0, some sort of uh, rate of emission, the rate of emission is never 0. This they were attributing to the process called as spontaneous emission, and the rest of the expression, which is correlating to the rate of emission, would be labeled as the stimulated emission. And in the later part of the lectures, what happened was we were trying to go to the process of the modeling of polarizations using the rule of transitions, where we found out about anisotropy as well as polarizations, and we were seeing how anisotropy is more favored than polarizations, and we were also trying to figure out mathematical expressions for calculating the anisotropy factor using the intensity of the light, which is parallel as well as perpendicular to the polarizer. So, in short, without the math being involved, this is the recap of whatever happened in the uh, past week four's lectures. So, before going to the problems, I'll just allow the room for 5 or 10 minutes for a brief uh, doubts session. If people have any doubts, they can shoot it out. By 3:20, time is 3:15 right now. So by 3:20, maybe we can start discussing the problems. Okay, we will get started with the sample problems. So, uh, as usual, I have kind of prepared a MCQ list of like around 8 MCQs, and then we have like basic, uh, two basic numerical problems which we'll be solving. So we'll get started. So question number one is, what is the fundamental reason that fluorescence emission can show a preferential polarization even if the emission process itself is isotropic? So we saw about isotropic and anisotropic emission processes. So what will be the fundamental reason that fluorescence emission can show a preferential polarization? So four options are given here. By the way, all of them, all the sample problems that I have prepared are actually MCQs. I couldn't find proper MSQs to actually prepare for. So only one option would be correct out of all of this. So option A is the molecules are physically held in a single direction by the solvent. Option B is photo selection where light preferentially excites molecules whose transition dipoles align with the incident polarization. Three is spontaneous emission is only possible in the direction of the electric field. And four is the wavelength of the emitted light is always shorter than the excitation. So all the hint is kind of pretty obvious here, I guess. So uh, except the right answer, I think in all the wrong answers, I've kind of kept a short hint, which will kind of make it uh, not make it the right answer. I would say. Anyone? Can you guess what the right answer is? Um, Spontaneous emission is only possible in the direction of the electric field, but we are uh, but two things are there. One is you might the answer might not be completely correct because even the direction of if the electric field of your this thing like molecules, if it is an angle with your polarization, then also you are getting some sort of fluorescence emission as well. And another one is uh, we are referring to emission here in a broader perspective, so it involves both spontaneous as well as simulated emission. So and just because we discussed this, three cannot be a right answer as well. And yeah, so we'll go over all the options as well. So one also cannot be a the right answer because in a solvent, if we are say, taking a liquid system, your molecules are not held in a single direction. They have much more freedom of movement than the molecules are aligned in solid state, for example. And in the option 4, the wavelength of the emitted light is always shorter than that of the excitation. That also might not be true because you also have other types of fluorescence emission processes where your excitation wavelength, the wavelength of the emission light is longer than the excitation wavelength as well, which is quite common, I would say, than the other process. So the correct option here is photo selection, where light preferentially excites molecules whose transition dipoles align with the incident polarization. So the alignment need not be exactly parallel to the electric field. Um, it can also be at an angle. It just should follow the cos square alpha rule. So is everyone clear with the answer? Yeah. Okay then. We'll go to the next question. So this is a pretty simple question. I was theoretical. In the formula for fluorescence anisotropy, which is your R, the almost the last concept that we saw in the week first lectures. What does the denominator, which is I parallel plus 2 into I perpendicular, physically represent? So I perp is basically your I perpendicular. I've just abbreviated it. So options are the average intensity of the ground state, the difference between absorption and emission, the total intensity emitted in all directions in 3D space, the intensity of the light source. Once again, this question, I think you might feel that two options are correct, but there is a small change. Like there is a small factor or a word, I would say, which doesn't validate one of the answers. So the options, I'll repeat once again very probably. The average intensity of the ground state. We have already only seen anisotropy for only two state interactions, where we have one ground state and one excited, like sir, where we have one a ground state and one excited state. So whether your denominator represents the average intensity of the ground state, or the difference between your absorption and emission processes, or the total intensity emitted in all directions in 3D space, or the intensity of the light source. So the uh, answer is option 3, which is the, so the denominator basically represents the total intensity emitted in all directions in 3D space. So this is a way of normalizing your differences in your parallel as well as your perpendicular light to give you a uniform anisotropy factor. I hope it's clear. So it's a pretty basic and theoretical question. So I'll go on to the next question. So the probability of an electronic transition rate is proportional to cos square alpha. What does alpha represent in this context? So the probability of an electronic transition rate is proportional to cos square alpha. What does alpha represent in this context? I think just now in question number one we discussed this question, discussed this concept basically. So options are the angle between the incident light and the detector, the angle between the transition dipole moment and the electric field of the light, the phase shift between the excitation and emission waves, and the angle of refraction in the cuvette surface. Two. Ah, yeah, it's correct. So its correct answer is the angle between the transition dipole moment and the electric field E naught of the light. Yeah. So I am hoping that the concept is pretty clear. So I'll go to the next question. Why is so this is a I think Uh, like this is a question you might be getting in your probably getting in your exams as well. Why is anisotropy generally preferred over polarization in molecular research? So why is anisotropy generally preferred over polarization in molecular research? Sorry, I don't know what happened there. But anyways, it's more theoretical and this thing. I think I already gave her the answer. So it's because the anisotropy, your anisotropy is mathematically more convenient. That's what we saw in the expressions as well. We defined at least the course instructor was able to define two expressions for anisotropy factor as well as your polarization. But he went on to tell that your anisotropy factor is more convenient mathematically for modeling your molecular rotations as well as you to process your polarization processes, basically to explain other optical phenomena as well. So I'll go on to the next question. Uh, which Einstein coefficient describes a process that occurs independently of the external radiation energy density? So this, I think it may be part of your I think your second lecture probably. So we defined four expressions arising from the Hamiltonian. And so we proceeded to expand the Hamiltonian. Hamiltonian based on the Einstein's phenomenological approach. Yes, Gopinath is correct. So he saved explanation from me. So it's A21, so which describes your spontaneous emission processes. So this happens independent of your external radiation energy density. I think a better key in this answer would be to just take a look at the process independently of the external radiation. Absorption doesn't happen, and stimulated emission also doesn't happen independently of this thing. So spontaneous emission, on the other hand, your spontaneous emission happens independent of the external radiation. So yeah, and yeah, this is a pretty simple question, I guess, repetitive question, I guess. If a sample is excited with vertically polarized light, the distribution of emitted photons typically follows which trigonometric relationship related to the excitation axis? So if a sample is excited with vertically polarized light, the distribution typically follows which trigonometric relationship related to the excitation axis? Yeah, cos square theta. So it's kind of pretty simple. So next question. What is the effect of photo selection on a randomly oriented sample of molecules in a solution? So just now in question number one, we discussed about photo selection, which is your selection of light molecules after polarization. So what is the effect of photo selection on a randomly oriented sample of molecules in a solution? So the options are, one second. Sorry. Sorry. Options are, it causes all molecules to align physically with the laser beam. Second option is, it selects a subpopulation of molecules that are oriented favorably related to the light's polarization. One second. Sorry. Third option is, it forces the molecules to emit light at a 90-degree angle only. Fourth option is, it eliminates the need for a detector filter. So which one of these options are true, or which one of these options is true? I think the question answers are pretty direct. Yes, uh, two is correct. So Your polarization basically, photo selection basically selects a subpopulation of molecules which is like favorable to the light's polarization angle. Yeah. And your last theoretical question, multiple choice question, which this is might be a application based, which will come later in your topics, but we'd like to discuss now as well. So, I think you guys are familiar with this process called FRET, which is your Foster resonance energy transfer, or some people would call it fluorescence resonance energy transfer as well. So, this FRET efficiency is determined by measuring the change in which property of the donor molecule. So basically in FRET what happens is you have a donor molecule and acceptor molecule next to each other, and donor molecule and acceptor molecule will have different excitation and emission energies. The If you shine a laser on the donor molecule, the energy will be transferred from the donor to the acceptor, and then the acceptor will be emitting a energy of different wavelength. Yeah. So this is kind of a optical sensing technique. So the question basically asks the FRET efficiency of this FRET is determined by measuring the change in which property of the donor molecule. So the options are mass, yes. So basically it measures the change in fluorescence intensity or lifetime, and then it measures the FRET efficiency. So the MCQs are done. So I'll go on to discuss the numerical problems. Yeah. So this might be some of the problems you might be getting in your exams. So a researcher excites a fluorescent protein with vertically polarized light. Using a set of polarizers before the detector, they measure an intensity of 240 units when the detector filter is parallel to the excitation and 60 units when it is perpendicular. So using these values, you have to calculate the anisotropy for the sample. It's a pretty simple problem where I have given just two values. You just have to add, subtract, and do all those calculations to find a common value. So I'll probably give time at least till one of you comes with an answer. So parallel, so the intensity is 240 units when the filter is parallel, and your intensity is detector filter is perpendicular. It's 60 units. So using these values, you have to calculate the anisotropy factor. So I think towards the last lecture, you would have gotten a formula for your fluorescence anisotropy factor using your parallel and perpendicular intensities. So using that, you have to calculate it. Is anyone able to come up with an answer for this problem? Anyone? I can give you a hint probably. So the anisotropy is obviously less than 1. So that will be the hint. Okay, we'll proceed to solve the answer. So basically, there is this one simple formula that we saw in the last class, last lecture of the week 4's lectures, where we saw that the isotropy factor R is given by this formula, I parallel minus I perpendicular divided by I parallel plus 2R, 2 into I perpendicular. So this was the formula that we saw. So I've just given that your I parallel is 240 units and I perpendicular is 260 units. So you just substitute all the values into this, and then you will get the value as R is equal to your isotropy factor as 0.5. So any range between this 0.49 to 0.51 will be your correct answer. So this is how you generally solve your numerical answer type questions. I hope this is Clear to everyone? If yes, we can move on to the next question. So the last sample problem I have for today is this. So two identical dye molecules are sitting in a rigid matrix. So molecule A and molecule B. So molecule A has this transition dipole moment oriented at 0 degree to the electric field, and molecule B has this transition dipole oriented at 60 degree to the same electric field. And determine, so we have to determine the ratio of the transition probability of molecule A to molecule B. How would you find that? So you can uh, read the question clearly. It's a simple expression once again. You just have to find the ratio. Uh, basically, you know, basically you know that the rate of basically you know the rate of transition of molecules, and you know the parameters which the rate of transition of the molecules is dependent on. And basically it even boils down even simpler when you're given the angles here. So you just have to do a simple mathematical function with the angles, and then you have to compare the ratio of those values with of molecule A to molecule B. So if you do that, what will you get as the answer? And transition dipole moment is also mentioned here. One is 0 degree, which is exactly parallel to the electric field. The other one is 60 degree, which is like 60 degree to the electric field. Yeah, 1 by 0.25. Yeah, 1 by 0.25. So that is the answer, which is basically 4. Um, and can you also put it in the chat box what expression did you use for that with the angles, if possible? Like, how did you come up with the 1 and 0.25 for molecule A and molecule B? Okay, so basically what we do is, so we know that the rate of transition is proportional to a specific parameter, which is the angle in which it is aligned to the electric field. So your rate of transition is proportional to the, yeah, Gopinath is correct, cos 2 theta. So your transition rate of transition is proportional to cos square alpha. So you just have to calculate, yeah, 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 cos square alpha. So you just have to do for molecule A and molecule B, you have to find out the cos square alpha, which will give you the values. So cos for molecule A it is cos square 0, because it's aligned at 0 degree. So cos square 0 will give you 1. And for molecule B, you have to use cos square 60 because it's aligned at 60 degree to the same electric field, which will give you 0.25. So the ratio will be 1 by 0.25, which is equal to 4. So, according to the numerical answer type questions, any value do you type between 3.99 to 4.01? This is with assumption that you will be allowed to type an answer with two decimal places. So, any answer with respect to, so ideally your answer should be 4.00. So, if we type 4.00, your answer will be correct, which will kind of fall into this range. So this is how you basically solve your uh, numerical answer type questions. So that is all the sample problems I have for today. Um, Apart from this, I'll just have another doubt session following which I'll just discuss the problems for week 2 as well. Um, yeah. I'll just pull up the slides for week 2. So I'll just give a 5-minute break. I'll just try to pull up the slides for the week 2's problem session, following which we can discuss them. Okay, so I'll just be skimming over the uh, so since the answers are already out, I'll try to uh, what to say skim over some of the answers, and we'll just sitting over some of the important answers, and sometimes we'll just be going over some of the important what to say numerical problems like this one. So the first question is, given that we use a polarizer of attenuation ratio of 1 is to 1000 and start with a plain polarized light along the vertical axis, say x-axis of 10 milliwatt. If we place polarizer such that the crystal axis is aligned along the y-axis, the amount of transmitted light that will be detected is defined as the percentage transmittance of unwanted crystal. So the loss in intensity of the light polarized along the vertical axis due to the polarizer is measured to be zero point 0.3 OD. So the answer here is, one second. So the answer here is 5 microwatt. So basically, how do you obtain the answer is basically you take the anti-logarithm of, so basically you find that transmittance of the sample, and after finding the so you basically to find the transmittance from the OD. So your OD is given here as point 0.3. So from the OD you have to find out the transmittance value, and from the transmittance value they have also given you the attenuation ratio. So if you apply the attenuation ratio as well as the OD, you will get out the loss in power, which is your 5 microwatt. So I'll go on to the next question. If we place n ideal polarizers, um, if you place n ideal polarizers, zero transmission of orthogonal. Oh, okay. Once again, sorry. I think I forgot to switch on my video. Yeah. Okay. So if we place n ideal polarizers, zero transmission of orthogonal axis polarization, and zero absorption for light polarization along the crystal axis, each placed at an angle 2 pi by n, then the intensity of light at the end of n such filter placement would be what? So this is also a pretty easy answer. So we know that we have a specific angle at which each filter is placed in, and the angle difference between each filter is 2 pi by n. So if we place this, I think this is a problem that we faced that I gave you guys as a first problem in the sample problems for the first week. So we were able to see that for one such filter, it was cos cos 2 power cos square alpha, and if we were able to do it for multiple such filters, it was cos square alpha the whole power n, which is basically cos alpha the whole power 2n, where n is the number of such filters. So the same concept you apply here. So you will be having cos alpha, alpha is 2 by n, the whole power 2n. The answer will be option A, cos cos of 2 by n, the whole power 2n. So the next question, the Hamiltonian operator for electron in an atom is, this is a multiple select question. So there are two options here. One is the most general definition, which is an energy operator, and one is the actual formula for the operator, Hamiltonian operator, comprising which energy units it comprises of. So the energy operator and P plus V into kinetic energy plus potential energy. So the fourth question. So if the ket vector A is given by x plus iy, then what is the bra vector A is given by? So we have to find out the opposite of the ket vector. So this is also, so your ket vector and the bra vector should multiply with each other should to give you a modulus kind of a operator, to give you the modulus of the ket vector. So basically the answer is, if you multiply something by some, if you multiply something by x plus y into something, it should give you x square plus y square as a result. So the only thing that could do here is two options, which is your option A and your option C. So the next question, identify the orthogonal bracket pairs from the following. So the first one is I sin theta, cos x plus I sin x and I cos x plus iy, x minus iy, x and ix. So the correct answer here is option C as option D, which is x and ix. So the sixth question, if d by dx were to represent an operator corresponding to a physical measurement and the state vector is given by exponential of ix, determine the bra vector corresponding to the resultant operation. So the ket vector is given by exponential of ix, which can be expanded into sin x plus I cos x as well. So we have to determine the bra vector corresponding to the resultant operation as well. So I think this is an MSQ. So anything you multiply it, you should give it the modulus of this. So the answer will be minus sin x plus I cos x, which is basically your uh, minus minus exponential of ix, and the other option is which is basically this one. Yeah. So basically your option A is the expansion of your option C. So both the answers will hold true. So in time seventh question, in time dependent perturbation theory, the perturbed and unperturbed Hamiltonians are independent, orthogonal, unrelated, and related through h naught plus h prime. So the answer is it's related through h naught and h prime. So the next question is a problem. So the energy of 1240 nanometer light photon is given by dash. That's the problem. Is basically the energy of 1240 nanometer light photon is given by dash. And here they have given us Planck's constant in electron volt second. So we also have to calculate the energy in electron volts. Electron volts. So how do we do that? So basically the answer is simple. We have to just substitute the formula E is equal to hc by lambda with the formula known values that we have. We already have the Planck's constant. We know C and we know the lambda value, which is given here. So we just have to substitute everything in this, and then we'll get energy as zero point 0.1 electron volt. So your energy ranges will fall between 0.99 and 1.01. Sorry, I think the answer is 1 electron volt. I think I mistakenly wrote it as zero point 0.1 electron volt. I'll change it later. So I hope this problem is clear. So I'll go on to the next question. So if 1 milliwatt of, yeah, thanks. So if 1 milliwatt of 1240 nanometer light photons are incident on photocathode of work function zero point 0.5 electron volt, the kinetic energy of the photoelectrons ejected from the photocathode would be what? So this is the continuation of the previous problem. So we already got to know that the energy is 1 electron volt, and in 1 electron volt the work function on uh, the work function is given as zero point 0.5 electron volt. So basically the kinetic energy is whatever energy that is, work function is the minimum energy that is required to excite the electrons. So if the work function itself is zero point 0.5 electron volts, then what will be the kinetic energy? So the kinetic energy will just be basically the remaining energy from the light light photons. So it will be 1 electron volt minus zero point 0.5 electron volts, which is basically your 0.5 electron volts. So your answer will be 0.5 electron volts. I'll go on to the next problem. If we were to represent the state of the coin as a superposition of uh, Hamiltonian get vector of sorry, not Hamiltonian, uh, get vector of heads and get vector of tails, what will be the value of the coefficient? So we all know in a normal coin toss, if we had to represent heads and tails, the value of the coefficient, the state of the coin will be half, because the state of the coin will basically be the probability. But if we are to have a superposition of both heads and tails, the probability will actually be squared. So probability of head squared and probability of tail squared will be 1. So the individual probability will be 1 by 2 the whole root, which will be 1 by root 2. So the answer will be 1 by root 2, or 1 by 2 the whole, the 1 by 2 power 0 0.5. I hope the answer to the question is clear, because a lot of people in the discussion forum also had the same doubt. I think a lot of people also mailed me saying that they had some confusion in this thing. So I also told them an explanation, but I am also explaining it here. And the next problem also should be solved by the same manner. So if the coin were to be biased and probability of heads becomes 0.75, the coefficient of tails will be, it's basically the probability of your tails, which will basically be once again, yeah. So so basically they are given a probability of heads will be 0.75. So what will be the coefficient of t? So the coefficient of t will be the square root of the probability of tails. So the probability of tails will be 1 minus 0.75, which will be 0.25. 0.25. So to find the coefficient of t, you have to take a square root of this 1 minus 0.25, which will be 0.5, which is 1 by 2. So the correct answer will be 1 by 2. Yeah. So I'll go on to the next question. I think the last four questions are just plot based questions. So those are kind of easier to answer, I think. So the plot of intensity of light against number of charges emitted gives a what? Gives what kind of a slope? Intensity of light against number of charges emitted. So answer is, I think, pretty straightforward. It gives a straight line with a positive slope, because the number of charges emitted is directly proportional. So your intensity of the light will be directly proportional to the number of charges emitted. More photons emitted, more light. But what about the plot of intensity of light against the kinetic energy of electron? So in this case, this will be a straight line with zero slope, which is parallel to the x-axis because the light is at the x-axis. So regardless of how much amount of energy is emitted, your kinetic energy will be constant. And the work function of the metal can be determined from the plot of what? So this also is a pretty straightforward question from all the concepts that we have learned. The correct answer is option number the frequency of incident light versus the kinetic energy, and x-intercept gives the work function. And the last question, in a plot of kinetic energy of emitted electrons is frequency of the incident electron, so what will be the uh, outcome? So basically you're plotting energy versus frequency. So the obvious thing is the slope you will be getting will be the Planck's constant. So the correct answer is option A. The slope gives the Planck's constant. So I hope everyone is clear with the questions that have been discussed, sample problems discussed, as well as the assignment answers discussed. So I'll leave the room in general. Time is, I think. So yeah, till 5 we have time for questions or doubts. So if you guys have any doubts, you can ask, or we can disperse the session where I'll see you in the next session for week 5. That will happen on the next Sunday, in 23rd of 22nd of February, from 3 p.m. to 5 p.m. Any doubts that you have? How to differentiate MSQ and MCQ questions? So basically, you will have how to put it in this way. So basically, your MCQ and MSQ questions you will be able to see. So MCQ questions you can only choose one option, whereas MSQ questions you will automatically be allowed to select multiple options. Yeah. So basically, there are two types of buttons for the answer keys. So one will be the radio buttons kind of thing, where you'll be allowed to only select one option. One will be the square buttons, where you can be allowed to select multiple answers for a certain question. So depending on that, you will be choosing either one answer or multiple answers. Yeah. I doubt that people will be the exam people who set the questions will be mentioning whether a certain question is an MCQ question or MSQ question. That is that you have to find out using the options that they are given. Whether they allow you to select multiple options at once, or whether they select you to allow you to choose only one option. Is that clear? All questions are allowed to select all options. That's right. I don't think so, because even in our NPTEL portal, if you had seen, I think some questions you would be allowed to choose only one option, and some other questions you will be allowed to choose multiple options as well. You could go and check probably one more time in the NPTEL portal as well. So the exact same format will be carried on to the main exam as well. Yeah, yeah, sure, sure. You can check and let me know. Probably in the discussion forum or in the next doubts clearing session, or sorry, TA session, you can let me know whether the same thing is happening. Then probably I'll also have an idea on how it's going. Any other doubts? Sure, sure. Yeah, sure. Thank you so much. Okay, if there are no doubts, I'll see you in the next session, Sunday at 22nd of February from 3 p.m. to 5 p.m.